Welcome to the video tutorial series about TBC drone photogrammetry. In this video here today, we will use the tutorial data from the DJI Phantom 4, which you can find on the geospatial.trimble.com page and here the Trimble Business Center tutorials. And when you scroll down, you will find here the section working with aerial photogrammetry. And then here, please download Processing DJI Aerial Survey Data. After downloading the data and unzipping the data, you will get following structure. You will have already a Trimble Business Center project file. Then there's a PDF where you have a step-by-step explanation how to run the data itself. And when you go into the data, you will find here the T02 file and the ground control point file and the raw data with the DJI Phantom 4 data images and also with the RTK data. And that's also why we will also work today with this part. We want to take a look how to handle RTK data in Trimble Business Center. Our goal, as always, is to make the video complementary to the PDF. That means when you open the PDF and you will go through these steps from the beginning, then we will also try to follow them. We will then here take a few parts and go more in detail, but you can also just run the PDF. The video wants to go a little bit more behind the scenes, explain what is here meant with some of these expressions, and also technology-wise what is happening in the background. We will fast forward very much through the project setup and take a closer look here how to import the data, mainly because we will here import the Rhinix OBS file, which in this case contains our Rhinix observations from the drone, and also the timestamp file with all the timestamps from the camera exposures, and also in this case here the JPEG files include here the positions of the drone, which are in a specific RTK format and status. When you typically have a DJI Phantom 4 RTK drone, these files are automatically written and they are stored as we have it here in our example where the images are located. So wherever you have stored your DJI images, then in this folder you will also find here this RTK data with it. And that's exactly how we need it. We will drag and drop this folder with the images and we will automatically detect that there are these files existing. So let's fast forward. We will quickly here run in fast mode the project setup, and then we will then take a closer look to the import itself. Okay, here we go. So there are now different ways to get this data of the images now into TBC. You can just drag and drop this folder in here. So this is really, I would say, the easiest part. If you are more a systematic person, then you could have here started first to change the coordinate system, what I just did. Then if you have multiple flights, you can then merge them. And then you can hit this button here where you have a folder selection. So instead of drag and drop, you would then here click this here, navigate here to the folder where these images are, and then hit the OK button, and it will fill out these fields automatically. Or even very, very classic home, import, and then you again go to the folder where the data is, and then you can import this part. Again, I will just here use the drag and drop solution, take this folder, and then the import dialog here on the right side will open up as we had it before, and it will automatically fill the focal length, pixel size, and height above ground. So what happens here in the background? In the end, what we are doing is we take here a couple images at the beginning and at the end and in between. We just open the JPEG images and then we search for the model name, which is written in the JPEG image in the EXIF header. And this model name is in a database existing here in TBC. So we automatically know now that this model name, which is in our case FC6310R, which is the DJI Phantom 4 RTK, and it's a unique model name for it. And therefore we know these are the important parameters from this camera. So as we want to show in this video here a little bit more detail, let's show this to you. You can take here one of these JPEG images, and then I can open this here, for example, with Öfern View, as shown in one of the previous videos. Hit I and E, and then we see here this model name. And this is exactly what we found, and therefore we know this is the DJI Phantom 4 RTK camera, and therefore the values here will be used. The EXIF header here has also some of these informations itself included. You see here there's the focal length also written in here, and then there's also in this case here the sensor size somewhere here, width and height. You see the pixel size is not here written in this part, but we have here the GPS information also, for example. The height above ground, which we can see here, is written in the DJI drones in the XMP tag. And that means you can just open a text editor with the JPEG image. And when you go into the text editor and you search for XMP, then you will find an ASCII related section in your JPEG image. And there we see the relative altitude, which is, in our case here, metric. So when we take a calculator, for example, and in the calculator we, let's see if I find one here. Yeah, we have one. And when we take now here, I'm not a feet person, so 1 geteilt durch 0,304. So if I take the factor of 3.28, which is 1 meter in feet, and then I multiply the whole thing with these about 80 meters, then I'm ending up at 262.46 feet, and no surprise, here we go, 262.49 feet. It's an average value from the different images that we have. Not every drone image has an XMP tag with the relative height, or in general the relative height somewhere stored. Therefore, for some other drones, for example micro drones, this field is empty, and then you can enter the height above ground yourself. Again, be aware, is it a feet or a metric project? Here in this user interface, you have to, in TBC, enter the height above ground in the unit that you are working with. And finally, the pixel size is stored in TBC directly for this sensor, for this drone. We stored this, and so we can then fill this out. You can always go and, if you say, I know it's not 2.41, but 2.40 or 2.41 for this camera here, and for whatever reason the sensor in the drone was not correctly measuring the height above ground, then you can enter yourself here manually a value and say, this is not 262, it's 250, 40 or whatever, but you can enter your own value here, and the same is also for the focal length. And this is the nice thing about the flexibility. We autofill here these parts. Also, what we offer is now that you manually can change these parameters, because they are the key parameters for a successful process of drones in TBC. Finally, we also know for some of the drones, because we already worked with the vendors together, where we can extract the GNSS quality. So in our case here, this drone data has already a high GNSS quality. That means if we open up again the XMP tag and then we scroll a little bit down, and we see in the DJI Phantom 4 an entry which is called RTK flag. And there is a white paper existing also where we have the different flag values, so they can be 16, 34, and 50. And 50 is the fixed solution for post-processed, which means that the values are in centimeter accuracy. You can a little bit also see it in the RTK standard deviations here, if they are really 1 centimeter accurate in position. This is perhaps more a relative value, but it's a high precision solution, and therefore we can enter here these values and use them in TBC for the processing with high precision. There's also an RTK flag 34, which is the floating solution, and this can vary something between 20-30 centimeters up to 2 meters. And then there's 16, which is data that is not post-processed, but it's capable to be used to run baseline processing. And this is the nice thing also here that we can offer. So in our case, this data, we will run the post-processing, but the data is already post-processed. But some people, they fly the drone without the post-processing, and then you can just use the data as it is here now and run in TBC the baseline processing, which will then, it's like a post-processing, and it will make the positions of our drones centimeter accurate. Important for us in TBC is, with this data, we can then, when we run, in this case here, our continuous process steps, which will then be, for example, the adjust photo stations, then this would here run the relative adjustment and automatically also run the absolute adjustment. And this is exactly what the text is mentioning. It says, so it enables us to run the absolute adjustment without a need of before running the baseline processing or measuring ground control points. We still will use the data here to run baseline processing just to show how it's done. And therefore here, this is the reason for this tutorial data that we have here. And then we can here show you how which functions you need to access to run it. Another nice thing is, if you have a large data set, let's say 1,000, 2,000 images, then to get this information is very fast, because we only open a few example images and extract from them the information. So you can here validate if everything is fine. When we hit then the import button, then all our images are imported. We are checking every single image for its status of its quality. And also what we do is check for these additional files. And this is what we will now see. We will now see that these files will be detected, and therefore in TBC, let's hit here import, a new dialog will open up. You see here some JXL entry that came at the beginning, because what we still do is we write everything together into one Trimble exchange format, and then we import this JXL into TBC, having all these values included. Here is now our information about the Rhinox file. We can see here is the Rhinox name, which is in this case a patched version. So we here check what Rhinox version is it. We in this case here just take care that everything is correctly written in the Rhinox. And we see also this is a continuous segment. Very important, this is not a static one, which is then typically when you have somewhere your base station on the ground. But we have here continuous data for our rover. The drone is our rover, and therefore we need this data for it, and also of course during the whole flying time. So from start to end we have here these timestamps existing. The antenna is automatically here assigned, so we know that this is now here DJI Phantom 4 RTK drone, and therefore we can here also take care of the antenna phase center and also how the corrections for the baseline processing can be applied. And then we have the receiver, and therefore the receiver, of course, is our rover, and this is then our kinematic survey mode that we have. So nothing needs to be changed, and we can hit OK to import, and then the images are imported. We generate pyramids. The first report warning I will not use, but then when the images are loaded, we will now take a look at the import report. So looking at the import report, we will now see here, let's drag it here, many informations giving us information about the drone data. So we have 219 images. They all have an EXIF header, they all have an XMP header, they all have RTK status. And we also see the RTK status is here 50. So we already have here seen this before, as I have shown in the text editor, but we want to here summarize the whole thing, and also that this is one camera that is used for this whole import. We also name the camera. So the camera model name that we found was the DJI FC6310 and R. And you remember I changed the pixel size and the relative altitude. So therefore here these used values are also listed. When we go down here, we can also see here the camera properties, how by default they would be. So in this case here 2.40. In this case here instead of 2.41. In the demo data, the T02 file is not in the directory, and so it was not found. If we would see the file, it would mention that we need to drag and drop the T02 file manually also afterwards. So just to give us also the information, hey look, there is a T02 file, please take care and import this one. Also, all images are fitting to the sensor size definitions, so there are no corrupt images or some other images that were perhaps wrongly copied into this part. And then just a summary saying, okay, we listed all these informations into the JXL, and then we imported all this here through the JXL into TPC. And also that we here generated the patched Rhinex OBS file. The error is in this case here because the receiver is unknown. It could also be a warning or a message, so please don't be here misled that this is something wrong. Okay, so whenever you close this, you can always access this again by right-clicking here this imported files folder, and then there's here the import report, and this will then again open here this file here, or this list here, and so you can always access it this way. At the moment, you see that the baseline processing is not possible because we have now the rover data and the kinematic data to it, but we need also the base station data, and in our data here, the tutorial data, this data is existing. We have here this T02 file, and we can just drag and drop this T02 file, and when you look here at the baseline processing part, as soon as we import this file here, let me just go here to show here that this is here now in R10, and we see it's a static part here. So this is now the data from our base station. Of course, the time has to cover the same time of our rover data. And when we hit OK, then the baseline processing here will then activate when this rover data is a control level size. Yeah? So we need to have here a base station that is of control quality, and therefore we can check this. You can go on the Project Explorer and to the points, then you scroll down to your point. You could also select it here, and then it will also be here. Then you expand the tree from this point, you right click it, say Properties, and then when you check here on these icons and you click one of them, then you see here the different quality standards, and it has to be of control quality. so that this can be used for our baseline processing. This is important for the baseline processing. So we have the static data from our base station, we have the kinematic data from our rover, and then we can here select to run the baseline processing. If you don't have a base station, there is also an option to download base station data through course stations or through other stations that are available depending from your region where you are. This can be available. It should be, if you do this within a range of up to 50 kilometers. The further you go away, the more the quality will suffer. So that means you will not reach any more the centimeter accuracy, and at some specific distance, then this is so uncertain that this will not be valid enough to use it for further processing in the drone photogrammetry. Concerning the baseline processing with an internet download, you can also take a look here at a video which is posted on YouTube called DJI Phantom 4 RTK TBC baseline processing with internet download, and here you see which steps you have to follow to download the course data, for example, to run here a baseline processing. Okay, so we are now ready to run the baseline processing. Let's just check first here also something about our RTK data. So here in the sessions, when we take here a look at the properties, we can now see this is our kinematic data, and which is in this case here to our rover, which is the Phantom 4 RTK. And when we look here below, then we see this is now not processed at the moment. So therefore, we will now run the baseline processing. Additionally, also, we have the Rhinex patched file here. So when we take a look at this one here, then we can see here, this is also continuous kinematic data. Also the, where is it, start and end time is here written again one more time. We see here also that every 0.2 seconds, so with 5 Hertz here, the data has been collected. And this is where we have this unknown manufacturer, where the error came. And then when we open this up here and we go into this one here, we can now see that the Rhinex data here is now the patched file. So this is now the Rhinex patched, is based on the antenna and the bottom of the antenna mount. So this is now here reduced here. So the antenna height is of course now 0. It's not at the antenna peak. I don't know how it's in English said, but it's at the mount of this data. Concerning the base station, we have now this T02 file, and in our case here we see now this is static, and also here the start and end time. Here the update rate was 1 second, but of course over a much longer period of time. And then also when we take a look here closer to it, then we can now see here type is also written here. Yeah, okay, it's twice so antenna information, but also here the antenna information a second time also written. And here we see now the satellites collected during this process, and also the antenna height, which is now coming through the T02 file, of course. Ready to go, we hit the process baseline, and now TBC starts directly to feed now the kinematic data and the part for the processing here. And when we look here, we see now the report button is grayed out. This is a little bit not so easy to understand. You have to click really the flash here at the beginning. And when you click this one here, you can then access here the report. In general, you would still see here that we have here 2,789 solutions. But we want a little bit more. We want to know how many fixed solutions we have, how many also floating we have, and then the report opens up here. And here we can now see, when we click here on the session details, that we have here 2,789 fixed solutions. And these solutions, they are all in the estimated accuracy of 0 to 5 centimeters, which is exactly what we want. You will not always get this solution. Sometimes when your base station, in this case here, does not have enough satellites, or it's a little bit further away from your area that you cover, then these values can also differ. But in general, we want to have here a large amount of fixed solutions. And you could also now go in much more detail. There is a great video tutorial about it, which explains how you can now take a look here at the different satellites. For me, what I'm a little bit here too naive, but I'm still looking here at the residuals, if they are here all within the range below 5 centimeter, and also in the different satellites. So I just scroll down and look if all of them are in a specific range. You see a couple of them are outside here of the 6 centimeters, and there would be now an option to remove this satellite if we want, or to cut out some areas that we don't want. But this is now really a very advanced part, and therefore we want not to go into this. We want here just to look at the summary itself. Up here, sorry. So this is then our estimated accuracy that we have. This is great, and therefore our baseline processing is successful. And if our data would have been an RTK16 DJI dataset, you remember this is when the data is RTK ready, but the post-processing is not done. Then when we will hit now save, then these images will be stored as post-processed and with a high accuracy in the GNSS, and therefore they will then be used for all our steps, for the relative orientation, for the absolute orientation, for the camera calibration. Will all the GNSS be considered and used for this part? If not, if you would have an RTK16 and you would not run the baseline processing, then we would only be able to run a relative orientation, and we would need control points to get our absolute orientation. As our data is already RTK50, so we are now just overwriting the high precision with another high precision solution. So hitting save is now overwriting the orientations of each single image. And when we now go to adjust photo station, we again get the information. We will now perform here a relative adjustment, and after the relative adjustment, as we see now here, this data includes RTK vectors and a processed trajectory, in our case not ground control points, and therefore we will then run an absolute adjustment automatically afterwards when the relative orientation adjustment is successful. And therefore this will then be our next step, but this will be explained in another video, so that this will not get too long. It's already very long. But let us just also look how you can access the baseline processing report. You can go into the Project Explorer. When you go to your session and you go here to this part, then you see here, this is my baseline processing report. And then when we access this one, we can again see the result of the baseline processing here. And this is now the extended one, as I mentioned, where you could even do some editing in this case here. But we will just here look at our first page, and then we can see here the results. Let's wait till it loads the data. Here we go, and there we can now see here that this has now successfully processed this part. When we go to the next page here, we can now see here our 2796 fixed solutions. And then of course all the other pages are now showing again these graphs that we have seen before. Additionally, also when we go to the properties here in this part, sorry, here into this one here, then we can now see that the processing status is now succeeded. So it's successful here, and therefore we were able to run a successful baseline processing. Okay, thank you for your patience for this very long video here. We will then in the next video run here the adjustment and then take a look here at the absolute orientation, and so the report file of the adjustment. And this is also very nicely, we will take a look at the workflow bulletin, which includes some graphs helping us also to make a better interpretation of this whole part. But no further ado, thank you very much for watching and have a nice day. Goodbye.